I'm presenting mainly what we have been doing during the last 4 years and the work in hydrologic modeling of the full catchment, water quality and water quantity. Our objectives was first to have a systematic database of the whole basin for the hydrological modeling, and then to build up a hydrological model to be able to have the water quality and water quantity for the full catchment, calibrate and calculate the uncertainty analysis for the hydrological model, incorporating the agricultural components in the model, and then finally having the impact assessment of scenarios of changes, mainly the demography, the climate change, and land use change. Well, as you see, the Black Sea is the sea between the sharing between the Asian and the European countries. 19 part or complete section of 19 different countries are within the catchment. The area of the catchment is more than 2.3 million square kilometer. More than 160 million people live there. And you see in the picture the major river basins in the catchment: the Danube, the Dniester, the Dnieper, Don, and the Turkish river basins. So quite a huge catchment, and I don't go to the detail of the SWAT model, the model that we use to model the hydrology of the basin. Anthony gave you a very short introduction on the SWAT. I mainly present the input of this model, what we use to build up this hydrological model. We used a very good resolution digital elevation map, 90 meter, and very good river network of the Green River. I think that was the first use of this river network for such a big catchment in 30 meter resolution. And then we have a few climate stations, temperature, precipitation distributed in the whole catchment, and the CRU data set, which is evenly distributed. Well, this is a combination of observed and statistics. And different land use map was available for the full catchment, and after different analysis we decided to use the MODIS, which is the basis for the land use change scenarios as well, and the soil data set from FAO. As you see, almost 63% of the whole catchment is covered with agriculture, so agriculture plays a main role in the whole catchment. So this is the temperature and precipitation distribution in the whole catchment. The average temperature goes from minus to around 15. And this is the average of 34 years from 1973 to 2006. And the precipitation distribution also, you have higher precipitation in the Alps and also in Georgia here, where it goes low in the Russian part, and here in Turkey. Also, 34 years average of precipitation. So these are the yield data, which are average yield globally available from Iraka 2000, which is the average yield around year 2005 years, I think, average. For the three major crops, the wheat, corn, and barley, and the harvested area also for the three major crops for the whole catchment used as an input. And for the water quality, unfortunately, there was not very good input data for nutrient loads in the catchment. So we came up with estimation of the nutrient loads to the surface water based on the population and the nutrients discharged to the surface water by the effluent of the water treatment plants based on the efficiency of the water treatment plants, and the untreated wastewater which is released to the ridges. So this is mainly based on the population and the efficiency of the wastewater treatment in different, and the percentage of the population that connected to the wastewater treatment plant. And here you see the contribution of different countries in having the loads to the surface water based on the population. It seems that Ukraine plays a major role. So these are mainly the input data of the model that we used, and SWAT has an option that you can choose in what level of detail you want to go to model your rivers, for example, in the model. So we tested different setups. So in a few setups you can have this threshold of the subdivisions of the catchment, so that you only have major rivers, for example, model. But we decided to go much more in detail to have all the rivers, even small rivers, in the basin model, because you can go always from the smaller scale and aggregate it to the rough resolution. So if you want to have a major river resource, you always can do that. And if you want to go and see what's going on in a small tributary, you can also do that. So we ended up having 12,982 subbasins in the whole catchment, and these subbasins are further divided into smaller units of calculation, which are called HRUs, or hydrological response units. And this is a unique combination of soil, land use, and slope. So this ended up to 89,202 HRUs, units of calculation. So we use SWAT 2009 to run and to have our simulations. We use the CRU data set, which is evenly distributed in the whole catchment, which we use the Modis land use cover. And the agricultural management was added to the hydrological model. And daily SWAT run and monthly output printing was chosen. I mean, the model will be run daily, and you can have the outputs daily. But because of the huge size of the project, we decided to have it, to print it out monthly, where if you have a huge resource, you can have it daily. 37 years of simulations, with considering the first 3 years as a warm-up period. And then these 37 years of simulations took 42 hours on a very good computer, very good resource to run. So that was the model setup, but it was not as easy as it seems, because there are always complications. So there were kind of many corrections to the model, mainly when you have, for example, observation in one river, and then you see that the model is not simulating much. And you see that this seems to be, for example, for Danube River, it's like having 9,000 cubic meter per second discharge. So, it's impossible that your model are kind of missing that. And when you go, you see that, well, if I can see, here probably. SWAT will put your monitoring point to the nearest river, and as we have very, very many detailed rivers there, so SWAT put it in the closest river nearby the outlet stations. And when you go to the Bing map to see, where is the location of your gauging stations, you see that yes, there is a small tributary there, but probably this gauging stations is for the Danube, which having many thousand discharge. And when you change the location to the right river, you see that yes, now you have kind of simulations for that. This is what I say as not imprecise locations of the information that you get as gauging stations. There are other complications, like you have reservoirs, you have water regulators, you have highly agricultural area. This is in Turkey, where you have many water abstraction, for example. And then for sure, when you're not including this information in your model, you can expect your model to reproduce the right thing. So these things need to be taken care of. And the glacier, of course, we had high altitude in many areas of the basins, and we needed to define, to very well parameterize these areas, the glacier, to have good results in the output. There were complications in rivers, where the river that you have is not matching the the DEM, for example, or the border of your basin, and there are some kind of disconnect in the river where it seems that your river system is not connected. So all these need to be taken care of once you build up your model. So after all those corrections, so we had our SWAT models, we had a few monitoring stations to see how well our model is working. So we have discharge stations, as you see, and nitrate monitoring stations, mainly on the Danube. So we set up our calibration. So we had our simulation from 1970s to 2006, and then we used 1973 to 2000 as calibration, and 2000 to 2006 as validation period. We have 79 stations of discharge and 37 stations of nitrate, mainly in Danube. So we parameterized the model based on the 25 very sensitive parameter, flow, nitrate, and crop yield. And so what is estimated is for having a round of calibration for 200 runs, it takes us 350 days to run. So it's quite impossible to calibrate such a model.
Unless the European Commission pays for an extension.
for a few years at least, yeah. So we came up with a solution of using and parallelizing first the code of the calibration so that it is possible to have it run or to calibrate it on a single machine in different cores or in a network of computers, which was quite successful, I think, that we ended up to have 200 runs in 2 weeks, where we used 4 blocks of 50 worker nodes. Thanks to Dorian Group, of course, in handling this. So finally, we got our calibrated SWAT model. I think that many people in this project waiting long for this. So we have, these are 2 examples for 2 monitoring stations in 2 rivers in the basin. First is a tributary of the Dnieper in Belarus, and the second one is Prut River. So we have observation. The blue line is observation. The red solid line is the best simulation based on the best parameter set that you have. But I want to emphasize that our result, our answer is not the best simulation. Is mainly the gray part, the range of uncertainty that we have. Because we cannot say that one parameter set which gives the closest answer to our observation is our observation. Our estimations are kind of uncertain. Our parameter, our model, conceptual uncertainties are there. So I think that there are a couple of good parameters which are resulting in a couple of, or a series of good answers. So our answer is the gray band. And there are kind of factors to see how well this is simulated, like the percentage of the observed data which is captured by this uncertainty band, and what is the thickness of the uncertainty band, for example. To see that the calibration and the validation period, the model do quite good in the validation part also. And these are 2 examples for the nitrate. Well, surprisingly, I can say that our estimation and the nutrient loads based on the population, it turned out really good. I can say that that was only an estimation, and we didn't have really a systematic information on nutrient loads. And we still have the dynamics, for example, of the nutrient loads in rivers, in 2 different rivers, and many other stations. This is what you see. This is the gap in the observation. Of course, the model can simulate, but there was no observation for 1 year, somewhere missing here. Also divided into calibration and validation period, and quite satisfactory results in terms of the p-factor and r-factor. So this was done for all the 116 stations in the catchment. The blue and green are the stations with good results, and the red ones are quite, I can say, bad results. And we explored a bit on the bad results. I mean, some are due to all the water management infrastructure that you had, and there's no chance to calibrate those stations without including the information. But some of the others are, especially for the water quality, is in the Danube Delta. I mean, up to here, all the simulations and observation matches very well the observation, but then in the Danube Delta, it seems that the concentration which is reported is even less than what is reported upstream. So it seems that it's kind of the concentrations is diluted in the delta, which cannot be captured by SWAT because it's not a wetland model. So the same up here in this station. So you see that the observations is much lower where the simulation says. So we think that there should be a separate model for wetland modeling to go more in detail for the nitrate estimation. So after we have this model and we validate our simulation results in all the monitoring points that we had in discharge and nitrate. So in many stations the simulations and observed were matched quite well. So now it's the time I mean, there are all kinds of analysis could be done. There are major rivers, and usually people are interested to see what are the loads, for example, from major rivers to the sea, or what are the discharge, for example, to the sea. Here is the example of the monthly discharge from the main rivers, the Don, Dnieper, Danube, and the Turkish river, for example. And the same for the nitrate, you have monthly loads for the major rivers. And here you can have what are the loads for all the river, including the major rivers. So yes, true, it's not only Danube who is which is contributing to the sea in terms of nitrate, for example, loads. So now all kinds of water resources analysis, like the green water and blue water, which are quite new in the literature. Green water storage is mainly the soil water and can be used as an information for agricultural needs. For rainfed agriculture, you want to see where you have more water to have rainfed agriculture, for example. And the picture that you see is mainly the 34 years average of the green water storage in the whole basin. You see where you have, for example, little soil water. So maybe if Turkey is doing like rain-fed agriculture here, might need to change the plan, for example. And not also the averages. I mean, these outputs are available monthly for the last 34 years. And it's also important to see what is the coefficient of variation of this parameter. And it seems that we could rely on these answers because I mean in the last 34 years there was not much change from temporal change, at least in the green water storage. What I want to emphasize here is again to have upper bound and lower bound of our uncertainty band, and we look at a range rather than a single number. So the lower uncertainty band says that, well, we will have the green water storage, for example, very little green water storage here. I mean, it is likely that we have this situation. The lower band says that, well, this is likely to happen. And the upper band says that, well, most of the catchment will have this amount of green water storage, except for the Turkish part, for example. And this is the median, where 50% of the simulations, for example, were below and 50% were above this amount. The green water flow is mainly the evapotranspiration. This is the water that you kind of miss and you cannot count on. And this is important to know where you have higher evapotranspiration. Again, the 34 years average and the variability. And the green water flow, the upper band, the lower band, and the median. Just go quickly. This is the blue water, which is your fresh available water. And you see where you have the maximum fresh water, same as the Alps and Georgian. And again, the coefficient of variation of this over time. And the blue water, lower band and upper band. What I want to say here is that when the lower bands say that you have enough water, for example, in the Alps, you can rely on this water because even the lower band says that it's, I mean, there are a lot of water here. And I think that when you have even your upper bound, which is very optimistic, for example, says that you will have water shortage, for example, here or in this part of Turkey, then, I mean, this is something that very likely happen. So this range could say us, I mean, this is not like exactly in Romania this happens, but this is a range that this might happen or this can go to the other side. And the average, the median. So the model results are available at sub-basin level and many variables even at HRU level. But to be able to compare it to the available observed data from FAO, for example, I aggregate them per country. And it seems that our simulations is doing quite well measuring the FAO data set. Except for Turkey, I see that it's kind of underestimating. But the thing is that not whole Turkey is part of the Black Sea catchment, while the FAO data set is an average for the whole country, and by this we are assuming that the same condition exists for the whole Turkey as it is for the part of the Black Sea. And this is also other water resources components: the blue water, green water, storage and flow, and the amount of precipitation in different countries. I go very quickly, and here is I mean, the maps are true, it's water scarcity. But the thing is that by definition, water scarcity is blue water per capita, so it's just the fresh water that is available per capita. So this is mainly the average, and this is the median and the lower and upper band. So the lower band says that, well, we will have severe water scarcity in many parts of the Black Sea catchment, while the upper bound says that, I mean, somewhere in Turkey there will be a severe water shortage. And I want to say that when the upper bound is saying that somewhere is shortage of water, I mean, this is really serious to look at. While, for example, you can rely on the water, which is even the lower band says that, well, we will have enough water in that place. But also it is, I mean, it's good to have vulnerable areas to be, I mean, if there is a change of management, for example, water management needed. So, and this is the water resources table per country, blue water, and also blue water per capita. And the one underlined, I forget to say that, yeah, this is the classification of the Falcon Mark when you have the red areas is the severe water stress, and the yellow area is the high water stress, where like bigger than 1700 you have available, water availability is quite good. And here is the underlined is the countries with high water stress. The other thing to look at is the monthly distribution of this, the green water and blue water components, because it's important to know, I mean, in which months of the year you have the highest soil water, for example, or you have the most evapotranspiration. I think this information could be used in many water management policy, or when you're setting your target, the soil water, how it changes. I just choose the four countries to look at, and what is your blue water, what is the best time to have, for example, water extraction from in different countries. And having this information on country basis, you can, I mean, it's very useful to have a big picture the policy that is going to be taken in this country. And here I more look at the different water quality components that we had. What is the nitrate leach below the soil profile? I mean, where is the vulnerable areas? And then the contribution of the nitrate contributed by HRU in the surface runoff, and the nitrate, for example, released to the reach, and among many other things and components of water cycle that you can look at in the whole basin. So I didn't bring all the outputs that I looked at, and this is the last thing that I wanted to end up my presentation with. This is something that came up earlier in the discussion. So we started here with the raw data, we processed the data, we tried to set up a model, and we think that now we have a high-priced information. But what goes next? I mean, it's a loop to have it and to change it to the knowledge, and then take it by the policymakers, and then have another round. So, I mean, this high-priced information will be, along with other societal benefit areas that, for example, GEOS has, like the economical, the social, the industrial, could be used to have a decision support system, and then change to knowledge that could be used by policymakers, by end users or stakeholders. And then the feedbacks again, and the needs, what are needed to be modeled, and then again. I hope that we don't get lost somewhere in this loop, in this project. So that was all from my side.
Is there any